Today we're going to look at absolute dating of carbon-14 notes. You know, it should be an orange sheet when you actually open it up. It says absolute dating notes, carbon-14, and what we'll be working on. So here's something familiar that we've seen from the last lesson. Radioactive decay data. We have our radioactive isotopes, which are right here, which are called the parents. Here's the parent right over here that are unstable. They disintegrate into the stable forms of these other elements, and this is the amount of time that it actually takes. So visually to look at it, here we have a rock, and you can't look at a rock and tell if it has uranium in it, or rubidium, or potassium, or anything else like that. We're just looking at it to show as an example of what this might look like on a subatomic level. So unstable atoms such as uranium eventually change into stable atoms such as lead. The original version is called the parent atom or the isotope. It goes into the new version, the stable form called the daughter atom. So if we have a rock right here and it has 1, 2, 3, 4, 5, 6, 7, 8 uraniums, if it undergoes one half-life, that means half of these uraniums are going to turn into lead. How do we know that? Look at our chart right here, uranium into lead. So half of these will turn into lead. So if we have 1, 2, 3, 4, 5, 6, 7, 8, 4 of those should turn into lead. And we do. 1, 2, 3, 4 have turned into lead. And any random one, doesn't really make a difference what it is. But now here's one half-life, the time it took to get half the amount of material from uranium into lead. According to the chart that we have, one half-life from uranium-238 to lead 206 takes 4,500,000,000 years. So 4,500,000,000 years. So if this was actually a rock and we found that the ratio is 1 to 1 right here, we would say, okay, it went through one half-life. And so now we know that this rock is 4,500,000,000 years old. Here's just another quick representation of, again, ignore this billion part of what it says down here for the actual ages. But here we have times 0 half-lives. We can go through here and count all the uranium. When it goes through one half-life, half these uranium will turn into lead. So after one half-life, T, one half-life, half of those have turned into lead. If it goes through another half-life, which would be T2, which would be second half-life, the remaining uraniums here will turn in, half of them will turn into lead. So if we do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So 15 divided by 2, I know it comes 7.5, but they'll probably make it into 8. So we should have roughly 8 yellow uraniums in the next one. 1, 2, 3, 4, 5, 6, 7, 8. Boom, works out. I know it's not exactly half, which is just an example of what's happening. If it goes through another half-life, half of these 8 uraniums will turn into leads, which would mean you would only have 4 left. After another half-life, which would be 3 half-lives, 1, 2, 3, 4. And this will continue on and on and on until, I don't know, never have total disintegration, but it will continue on for all that amount of time. We can graphically look at this breakdown or disintegration of the isotope into the stable element. So here's the parent isotope. It's going to be the red, and the daughter's the green. So what does all that mean? If we take a quick look right here, 0 half-lives, we have a bunch of red dots that represent the parent isotope, and you have a full amount. No half-lives have happened. If after one half-life, half of these red circles would turn into the daughter product, which in this example turns green. So here we have half green and half red, which is half parent, half daughter. If it goes through another half-life, the remaining red should be halved, and then that's what happens here. And this, again, will continue going on. If we were to graph this data, you'd have something that would look like this. So you start off with 100% of the isotope, and that means at the same time, 0, you have 0 daughter. You can pick 2 points right there. You plot the data. After after one half-life, you have 50%, and the corresponding daughter elements goes to 50. So boom, they meet together right here at 50%. Where they cross right here, anytime you see two lines that look like this and they cross, that represents the first half-life. And then you have the continuation of the decay down here. And for every decay, there is a corresponding daughter element on the other side. So this is what this graph is all about. Here's just another example of what's happening right here. We don't have the daughter one in this one, but nonetheless, they're showing that the proportion of parent atoms remaining, if the dark ones are parent and the red ones are daughter. If you start off right here, 100% are all blacks. Here there's 20 black dots, so those are 20 parents, 0 daughter. After one half-life, you have 10 black dots, which would be 10 parent atoms, and then 10 daughters. So 10 plus 10 is going to be equal to 20. Then we go through another half-life. So we have 10, which becomes 5. And whatever is transferred over, it goes over to the daughter, which would be 15. If we add up 5 and 15, that gives us 20. If we take half of 5, which gives us 2.5, the remainder becomes the daughter, which is 17.5. We add up 2.5 and 17.5, it gives us 20. So we're starting off with 20, I don't know if that really doesn't really say what it is, let's say 20 grams of this new mineral right here. And as it slowly decays, or disintegrates, you have more stable daughter products being formed. We can do this on a chart. So we're going to go through how we actually calculate how old something is. Looking at this example, and you're going to use this example as a model for your homework for tonight. And we'll take a look at your homework before you guys actually split. So here we're going to look at carbon-14, again, which is used only for organic materials. Skin, hair, teeth, shells. And they might have carbon-14 in it, disintegrating into nitrogen-14. So radiometric decay of carbon-14 to nitrogen-14, 5.7 times 10 to the third years is 5,700 years. Sometimes you'll see 5,730 years, but we're going to ignore that. We're going to stick with 5,700 years as we go through this. So in our example, if we have 0 half-lives, and we have 100 grams of unstable carbon-14, the percentage of stable nitrogen-14 is going to be 0, and the number of years that have actually went through is going to be 0, because nothing's happened, no half-life. So if we go through one half-life, boom, one half-life, what does that mean? That means we've halved the original amount of carbon-14. So we take a 100 divided by 2, and that gives us 50. Oh, sorry. Gives us 50. So 100, one half-life goes down to 50. So what happened to the other 50? The other 50 became the stable nitrogen. So how do we do this one? Well, if there was 50 and they dropped out, well, we start off 100. 50 went over to the other side. So now we have 50. So 50, 50. How long did that actually take? Well, if that was one half-life, and it tells us right here one half-life takes 5,700 years, that actually took 5,700 years. Notice if we add 50 plus 50, it gives us 100, which should be our parent, where we started from. If these go through a second half-life, okay, so here is the unstable parent. We need to break that into half. So what is 50 cut into half? 50 divided by 2 gives us 25. What happened to the other remaining stuff? It became nitrogen-14. So if we had 100 and now we take away 25, that represents 75 atoms of nitrogen-14. How long did that take? It took another 5,700 years. So one half-life was 5,700 years. It took another one. So we add another round. And it comes to 11,400 years. So whatever we're measuring, this organic material, and we have this ratio of 1 to 3, just think of like quarters and stuff like that, the sample would be 11,400 years. If it goes through another half-life, so we take half of 25, so 25 divided by 2. And remember, you have a calculator on your computer if you've left yours at school, or you can find one online, just go to Google. So 12.5 grams is what we have the original. Whatever switched over went to nitrogen. So we do 100, subtract 12.5, and now we have 87.5 grams of nitrogen 14. How many half-lives did that take? Now we're at 3 half-lives, so we need to do 5,700 plus 5,700 plus 5,700, and that gives us, the sample is going to be 17,100 years old. After the 4th half-life, so now we take half of 12.5. So 12.5, we're going to divide that by 2. That's going to give us 6.25. So 6.25 grams of what we have left. Whatever is decayed or disintegrates goes into the stable daughter. So if we start off with 100, and now we only have 6.25 left, that means 93.7 grams are nitrogen 14 within the sample. That took 4 half-lives, so 5,700 plus 5,700 plus 5,700 plus 5,700. Sample is 22,800 years old. If it goes through another half-life, so now we take 6.25, so 6.25 divided by 2, and what you're going to put in this box right here is 3.125. Well, if we're at 3.215, the other stuff is transferred over and disintegrated into the more stable form into nitrogen 14. We pick 100, subtract 3.125, and that means 96.875 grams in this particular sample is going to be nitrogen 14. How long did that take? Well, here we have 5 half-lives. I'm going to save everyone the trouble. If we do 5,700 times 5, we're going to get a year that it took 28,000 years, or we are at 28,000 years. 20,500 years is how old the sample is. I kept on using 100 because that's what we started for, so make sure you're careful in your homework that when you go through this, you kind of see what's going on, that these numbers will change. But hopefully you see the pattern right here. This each time is going down by half, so half of 100 is 50, half of 50 is 25, half of 25 is 12.5, so on and so forth. Whatever's breaking down or disintegrating is becoming the stable part. So now this is 50, 75, 87.5, 93.75, so on and so forth. So this is how this chart works. This is the data table that we filled in. So when we talk about carbon-14 disintegrating into nitrogen-14 takes 5,700 years, we're able to find out, looking at the percentages, and that's something you'll see in the answer key on Friday, of how does this tell us how old something is. So for your homework tonight is what you need to do is you're going to go to your day 4 of our next assignment, and you'll see radioactive dating homework student. It's going to be a purple sheet. Radioactive decay. It says directions. Fill in the chart below to show how scientists use radioactive decay to determine the absolute age of a rock. So in this one right here, you're looking at rubidium to strontium. So here's rubidium to strontium. Again, keeping what we kind of used today as a model of how to fill in the rest of this. Then you go down to the second page, directions, fill in the chart below to show how scientists use radioactive decay to determine the absolute age of a rock. And then you look at this diagram right here. This one, you were actually looking at uranium-238 to lead-206. So uranium-238 to lead-206. So 4.5 times 10 to the, we have a boo-boo right there, make that to a 9, is actually going to be 4,500,000,000 years old for that one. So again, go through, look at the example that we did in class, or at least we watched in the video, and that will help you out to see what's going on. And I'll post the answers on Friday. Okay? If you have any questions, make sure you make a public comment in Google Classroom. Make sure you watch the video again. Make sure you read the actual layout of what you're supposed to be doing every day. And then please ask if you have any questions. Take it easy.